So now we've prepared the molecular replacement models, it's time to do some molecular replacement and prepare to do that. So let's make a new CCP4 project. CCP4 1. And some people keep the data file in the same place. I'll make a copy. Data files. Not there. Okay, so that is our MTZ file. If we look at it, it is P41, and we need to do a molecular replacement in P41 and P43. Now, the programs will change the space group, but I want to make a version where I run the program twice in the two different space groups. So let's copy that to P41, so we're absolutely sure of the space group. Oops. And then let's make a new put the sequence in here for convenience. So we have the sequence and the data, which should be enough for, and the model is in the other directory, so that should be enough for molecular replacement. So let's make a new project. Rep. So let's create the new P43 file. We want to re-index it. There should be a I've forgotten the name of the re-index. Okay, P41. We'll call it P43. So the I information and the HKLs are exactly the same. It's just that the header has changed. Okay, now I happen to know that PSB28 is a dimer, and if we look at the space group diagram for P41, we will see that there are no crystallographic two-fold axes, which means that the protein, there must be at least two in the asymmetric unit with a two-fold axis. So there can't be a molecule that is forming a symmetry mate, a dimeric symmetry mate, with itself. Let's do some more analysis. If we look at the contents of the unit cell, the size of the unit cell, we can calculate something called the Matthews coefficient, which is the Daltons of the proton per cubic angstrom, or is it cubic angstroms per Dalton of protein? I can never remember, but the important thing is to look at the solvent content of the crystal. So if we take the MTZ, it will extract the unit cell information, and we can use we know how much protein is in our molecule, and then we can analyse the solvent content. So if we do that, we see that, how do I rescale? Let's look at the log file. Okay, so looking at this, if there is one molecule in the unit cell, it is 90% solvent, and this is the probability of that is very low. We know the protein is a dimer, so there must be at least 2 in the asymmetric unit, unless something weird is going on. So if we look for there are 2, that's still 0 probability. Now on the right is the total probability, here is the probability weighted by resolution. So lower resolution structures tend to have higher solvent contents. Typical protein crystal is about 50% solvent. So if we look, we have for 4, that's 27% probability, and 5 is 58%. So according to this model, there are most likely to be 5 molecules in the asymmetric unit. However, from symmetry considerations, I think 5 is unlikely. It's most likely to be 4. Now this is annoying because the more there are in the asymmetric unit, the harder they are to find, because there is less Patterson correlation to pick up on. Okay, so we're going to have to look for probably 4, but it may be 2, or it might even be 6. We don't know at this point. The other thing to calculate, which most people don't do these days, is a self-rotation function. So this is a measure of the internal symmetry of the Patterson function. Peaks in the self-rotation function correspond to, let's just leave all defaults. Peaks in this function correspond to symmetry axes. So we see one big peak, which is the crystallographic peak, and then we see, if there are other symmetry axes, we can see peaks for those. So if we look at this, this is the self-rotation function. We see the big crystallographic peak in the middle, and then round the side there are other off-axis peaks. So these, some of these, this is a crystallographic peak, but this is off the axis. So that there is significant non-crystallographic symmetry in this. Let's look at the actual log file. Okay, so these are the rotation function peaks. 0, 0, 0 is the origin peak, and there's another peak, 54% of the origin, with a chi polar angle of 180, which means this is a twofold axis. And then there is another one, 29%, 180, another twofold. And then there are other, this one is nearly as significant, also a twofold. So there are 2 quite big non-crystallographic twofolds, so there are probably 2 dimers in the asymmetric unit. So we get that from the self-rotation function and the predicted solvent content. Okay, let's do molecular replacement. So I'll use 2 cores. Our MTZ in will be, we'll try it with P41, and we will search with our chainsaw model. The sequence identity was about 60%. NMR models tend to be less accurate, so let's put that in as an RMSD of 3 angstroms. So this weights the likelihood function in phasor. If the molecular replacement is an easy one, it doesn't matter what you put in here. If it's tricky, you should put in a realistic value. Right, so that's our ensemble, and then we're going to search for ensemble 1, and let's search for a dimer. So in phasor, if you search for multiple copies, it can do a complicated search, and if the results are weak, that can take a very long time. So search for a dimer should be quick, and we'll do that in P41. And our option is to run in the MTZ space group, P41 dimer. I'll run that. And then let's run the same job again, but in the other space group. So I can do this, I can change this option in phasor, but I want to do it in here at the MTZ file level, because later on one of these will give the right solution, and I just want to continue working with that file. If Phaser has to change the space group, you need to re-index at some point anyway, so I just want to re-index right at the beginning. Okay, so now I'm searching in P43 for a dimer, and set that going, and these will take about half an hour each, so I'll pause now.